Okay.
But you may want to take it just as a practice. And oops, sorry. If so, that just to improve your understanding. Okay, let's see if there are no more. Oh, I guess I should just make sure everyone's clear on. Sorry about this. This is kind of a painful thing, I guess. Just want to go over this thing one more time. No, not that. Oh, no, I don't need to go through that. That's fine. Okay, so today what we want to go over is, so far we talked about the differences between imaging and non-imaging optics. And then we talked about a particular case of a simplified version of the ideal non-imaging optic, which is the compound parabolic concentrator, or the CPC. And we saw that in the two-dimensional universe, the CPC is an ideal concentrator. In other words, it's a 100% efficient concentrator. Of course, and I told you, in 3 dimensions, this is no longer true. And then we also learned about how to design the CPC. So just, I want to make sure we are clear on that. So I'm going to go back to this, just highlight a couple of things which you really should be aware of. Sorry. Is, first of all, there is an acceptance angle, theta, defined by the geometry of the CPC, such that below any rays coming in less than theta will get 100% accepted, and any angles beyond the theta will not be accepted. So that's an important condition. And then we define the concentration factor as the ratio of the input aperture here, A1, divided by the output aperture, A2. Okay, A1 over A2, and we derive this expression. So the concentration factor now is inversely proportional to the acceptance angle. In other words, if you want a lot of concentration, you can only collect a small cone angle coming in. If you want to collect a large cone angle, you can only concentrate a little bit. So it's a trade-off, and this is a very fundamental trade-off. We'll come back to this point many times during this class. The other thing that we derived had to do with the actual geometry of the CPC, which is, how do you calculate the height of the CPC? And we estimated that the height of the CPC is something like, the input aperture times 1 plus sine theta over 2 tan theta. Again, you don't need to memorize any of this. You can just look it up. But just keep in mind that if you try to concentrate a lot, the height of the CPC has to increase. In fact, it goes up dramatically. Okay. Now, with that in mind, now we are going into 3 dimensions, the real world, and we're going to do a little bit of math. So to understand how CPC concentrates and why is it considered optimal. Okay. So the CPC maximizes concentration. To show this, let's look at a very simple example shown here. So in this picture, what do we have? I'm going to zoom in. First, we have a cylindrical black body at some temperature T, which is here. Okay. And we're going to assume a cylindrical black body, which is infinitely long. So that's what these dots mean. It's infinitely long. And that's just to simplify the math. We'll come to the more complex case soon. It has a radius R, indicated by here. Okay. And then we're going to look at, and we're going to call it SR as a label. Okay. And then we are going to look at 1 unit length. Let's call it 1 meter of the cylindrical black body. And it's at a temperature T. Now, of course, it is emitting light, photons, because it's at some temperature. It's a black body. We know it emits with some spectrum. Okay. Now, on the other side, what we're interested in is we're going to collect this light with the concentrator. And we're going to think about a linear concentrator for simplicity, who's a concentration factor of C. So what does that mean? That means we have a concentrator, which is, again, infinitely long in that dimension. And then its input aperture is here. And it collects the light into the output aperture, which is here. Okay, again, infinitely long, so we're taking a slice of it. Okay, so again, we're thinking about this as a CPC. We'll draw this in 2 dimensions shortly for simplicity. So this is A1, A2, same as before. Okay, now, and we're going to assume this, both of these are embedded in a universe, in space, basically at 0 Kelvin. Okay, so far so good. That's just defining the problem. Now, total flux emitted by a black body of a given area dA and a temperature T into a hemisphere, because first of all, this is going to emit in all directions, right? And that is going to simply emit with cylindrical waves going out, basically, right? And in fact, it will go into the full sphere. So this should not be a hemisphere. This should be a full sphere. That's a mistake. It's given by d phi. I'm going to cross that out. Sigma t raised to 4 times its area. Now, sigma is the Stefan-Boltzmann constant. We know that. T is the temperature, and dA is the area of interest of the surface. Now we can plug in, if we assume a black body of length LU, it emits, we can calculate the area dA. dA is the surface area, is simply the LU, which is the length of the cylinder, multiplied by the circumference of the cylinder, 2 pi r. So that gives me the total area of emission from the cylinder. And I plug that in, I get this relatively simple expression. If we use 2 pi r sigma t raised to 4 LU. Now I can make LU equals 1 because it's an infinite element. I'm going to, infinite black body, I'm going to assume, okay, what is my emission per unit length as a metric? And I can simply set LU equals 0 and, LU equals 1, and then I get that. Okay, so far so good. Now I'm going to look at the simplified view. I have a top view, so exact same geometry as before, but I'm just looking at it top down, taking a slice through the cylinder. Again, I have my source on this side. I have my concentrator on this side. Okay. The amount of radiation. So first of all, keep in mind that this whole thing is emitting totally per unit length, sigma t raised to 4 times 2 pi r. Okay, that's the entire thing. Now, of course, if you look at some distance way out here, which has the distance d as shown here, small d, I have an area of a cylinder on this surface of 2 pi d times its distance, so length. I'm going to just use unit length for the sake of argument because we're going to just think about unit lengths for now. So I can drop that. So I get 2 pi d as its area. Now, how much energy is spread over that area is given by the total energy, sigma t raised to 4 times 2 pi r divided by the total surface area of the outside cylinder, 2 pi d. Now, that's the entire thing, right? So in other words, that is the entire thing over this entire cylindrical surface. But what I am only intercepting is this tiny area corresponding to the CPC, right? So I have to now multiply by its area, which is the input aperture area. So I'm multiplying that by A1. So that's the fraction of the energy that I'm intercepting with the CPC. So that's how I get this expression. Okay, so again, I have a black body, cylindrical black body. It's emitting light out, spread over a very big cylindrical surface, and I'm capturing a small portion of it with the CPC of input aperture A1. Okay, so far so good. Now we're going to assume that this the black body. So at the exit aperture of the CPC, we're going to assume there is a black body whose area is A2, as shown there, and it is also a black body. It's like a solar cell or water heater or some receiver that has to be at a temperature which is less than T, because the only thing it's getting energy from is the source. It cannot be a higher temperature than T. But if we assume equilibrium as steady state, then it has to reach the same temperature T as the source. Okay, then, and that's equilibrium condition. So in other words, nothing is happening, everything is steady state. In this case, this black body will also emit the radiation with a flux per unit length, given by the exact same expression as before, but now its area has changed. It becomes A2. Again, we're talking about unit length here, so that A2 has to be multiplied by 1 in the dimension into this screen. But let's ignore that because it's just 1. So now under thermal equilibrium, when they are both at the same temperature, you have to assume that the flux entering the CPC must be equal to the flux exiting the CPC. Again, we are assuming that all the flux emitted by this is going in only in that direction and it's exiting the CPC. So this condition becomes true, and then we can equate these two expressions, okay, because they are the same. They have to equilibrate at steady state. Otherwise, one will be gaining heat and another will be losing heat. And so we're assuming that's not steady state. So this is equilibrium. Then we come up with a very simple expression that we saw before, that A2 A1 divided by A2, which is the concentration factor, is now 1 over sin theta. Here we derived this without knowing anything about the CPC. The only thing we did, we assumed Stafford-Boltzmann law to assume that the black body, how is the flux related to temperature. And the second thing we assumed was equilibrium, thermal equilibrium, and that again comes from the second law of thermodynamics. So we derived this expression without knowing anything about the concentrator. This can be a black box here. This doesn't need to be a CPC because I did not impose any constraints on it. But we'll get the exact same expression as what we derived in the last class, where we assume the geometry of the CPC. So this is one way to show that the CPC achieves what is thermodynamically possible as a maximum in terms of concentration. So this is another way to prove that the CPC is optimal in 2D. Okay, that's just a matter of semantics, but it's useful to think about it that way. Now, we want to also wrap this concept a little bit. So let's go through this one more time. So since the rest of the space is 0 Kelvin, any radiation leaving A1, which is the CPC here, and coming from A2 can only be going to the source here, because there's nothing else in this particular universe as we have defined it. This implies also that the acceptance angles of the CPC with the entrance aperture A1 cannot be larger than the theta shown here. Now, what is theta? Which, by the way, I forgot to derive it out here. I just said theta here, but we didn't say what the theta is. But the theta, of course, so let me rewrite this equation, A1 over A2, which is, of course, a concentration factor, is D over R, or 1 over R over D, 1 over sine theta. So, of course, R is the radius, D is the distance, and that is the theta. Sine theta is R over D, as you can see there, right? So that's where that comes from. So this is another way to say that the acceptance angle of the CPC with an entrance aperture A1 cannot be larger than theta. Now, we of course assume as D goes to infinity for a constant theta. This is, for example, the situation of the sun. The R also goes to infinity, maintaining that ratio, as we can imagine. Then A1 becomes a straight line, and the concentration factor simply becomes A1 over A2. Now, what does that mean? It's just a detail, not terribly important, but if we were to zoom in here, I told you this is a curve, so I'm going to exaggerate that curve. But if that D is very big, that curve essentially becomes flat. So this now becomes the entrance aperture of the CPC, becomes a line as opposed to a curve. That's all that's saying. Just a detail, not terribly critical for our purposes, but just for completion. Again, this is the maximum possible concentration for a 2D CPC. Same, so CPC gives the maximum concentration in 2D. Okay, so it's the same thing as I said before. Now let's think about 3 dimensions. In 3 dimensions, of course, the source is now a sphere, a simplified source. That's again the sun. It has a radius r. Now we can define solid angles because angles in 3 dimensions have two axes. So we have an axis like that, we have an axis like that, as you see here, and that's defined by solid angles. We won't go into a great detail on how solid angles are defined, at least for now. We might get into it later. And of course, the concentrator itself is also 2-dimensional, and we're going to assume a concentrator on Earth. It has an input aperture A1, an output aperture or an exit aperture A2. Now, the flux emitted by the source is from Stefan-Boltzmann law is area multiplied by sigma multiplied by t to the power 4, and the surface area of the sphere is simply 4 pi r squared. Okay, it's emitting in all spherical direction. The radiation captured by the entrance aperture A1, just like before, so keep in mind that this sphere is going to emit over a huge spherical volume, but only a portion of it is captured over here. So we need to find that fraction. And that fraction is found by taking this ratio, 4 pi r squared by 4 pi d squared, which is where d is the distance from the center to the center to the aperture, and multiplying by the entrance aperture of the CPC, just like before, right? So we get a relatively similar expression here, r over d squared, sigma t raised to 4 times A1. Okay, so far so good. We're again, just the vertical cut is shown on the top, just to reiterate this point. Again, this energy that's captured at A1 is concentrated onto a black body at the exit aperture A2, and thermal equilibrium, just where before, the black body or the solar cell at the exit aperture heats up to a temperature T, and the radiation that A2 emit must also equal that it receives. So what it emits is here, and this is what it receives, which we just calculated from before. They have to equal, as we know, and we get a relatively simple expression. Okay, here, okay, the 4 pi cancels out, as we know, sigma t raised to 4 cancels out, and all we get is A1 over A2, which is a concentration factor, is d over r squared. This is a very beautiful equation because now it tells you that the concentration in 3 dimensions is simply inversely proportional to sine squared theta. So just to summarize our understanding, concentration, again, this is the maximum in 3 dimensions, is 1 over sine squared theta. Concentration in 2 dimensions is 1 over sine theta. So it's a dimensional difference. Now, again, just like before, as d goes to infinity, r also goes to infinity, maintaining that angle, so constant theta, and then this A1 tends to be a flat surface. So instead of being this curved portion of a sphere, it just becomes a plane. So it's just a way to think about it, but not terribly important. So let's keep going. But now you get a very nice, simple expression that the concentration factor is proportional to square of the acceptance angle. So it's a little bit worse if you're trying to concentrate more, your acceptance angle is even more constrained. Now, one really cool thing that happens is that you can actually get even more concentration by taking advantage of the fact that the Stefan-Boltzmann law actually now depends on refractive index of the material. In most cases, we'll deal with air, so the refractive index is 1, so there's nothing you can do about it. But in some cases, you can actually immerse the CPC in some material whose refractive index is greater than 1. So just to see this, the expression for the Stefan-Boltzmann constant is relatively complicated, as shown here. Of course, you don't need to know it, but the fact is that you can write this as n squared, where n is the refractive index, multiplied by sigma v, where sigma v is the Stefan-Boltzmann constant in the vacuum. So this n square is what we're most interested in. This implies that I can plug this into the equations from the last slide, which is shown here. So keep in mind that the source is still in vacuum, but now we are assuming that the solar cell, or the CPC, the exit aperture of the CPC is immersed in some material of refractive index n. Okay, so again, we plug in the expression from before. So this is the flux that's received by the CPC. This is in vacuum, so no n. Whereas this is the flux that's emitted, which is not in vacuum. It has some refractive index n, so you have an extra n there. Now, what does that mean? That means my concentration factor, A1 over A2, now becomes n squared over sine squared theta. This is quite nice, right? So that means my concentration factor now goes as n over sine theta squared. So because n is typically, a number larger than 1, in all cases, you can actually increase the concentration factor by immersing the solar cell in some material whose index is greater than 1. So it's a relatively simple idea to improve your concentration factor. Another way to think about it, you can, for the same concentration factor, you can increase your acceptance angle as well. And you can do the same derivation in 2 dimensions and you get the expression as shown here. As expected, it just goes as n over sine theta. So this is all relatively intuitive. Now you can also look at this from Snell's law, what we just derived using thermodynamics. Again, everything is consistent. So in Snell's law, we know that if you come in at an angle theta to the normal, so the angle here is theta, I would bend here at an angle theta star, such that theta star is less than theta, and it obeys Snell's law, right? So this is Snell's law, as we all know. And we can do the exact same derivation as before, and you end up with an expression that A1 sine theta prime is equal to A2, or A1 over A2 is now equal to 1 over sine theta prime, which is nothing other than n over sine theta. So what has happened here is that for the same concentration factor, I've increased my acceptance angle simply by filling my CPC with some material of refractive index n, which is greater than 1. So that's a cool trick that you can do to increase either the increase acceptance angle or increase the concentration factor. Now,